Hello. So this talk will be about minimizing the interference in asymmetric sensor network. This is a joint work with Karim Abu Afash and Mattia Katz. So I will start by giving a short introduction to the settings and then I will present the problem and our result. Then it will be followed by the problem in 1D and the problem in 2D. Okay, so let's start with a short introduction. So given a set P of sensor in the plane, a range assignment for P is a function rho from P to the real number, to the positive real number, that assign each sensor a transmission range, which is a radius. Okay, so we can think about we have a sensor and we have its range, and everything inside this range is its transmission area. The induced directed communication graph, G rho, for the set of sensor P, with a set of edges E rho, where E rho is all the edges V to U, such that the radius assigned to V, the range that is assigned to V, is bigger or equal than the distance between V and U. So here is an example of induced directed communication graph. So the model that we just described is the asymmetric model, which means that given a set P of sensor in the plane, each sensor P in P is assigned a transmission range rho of P. So the asymmetric model, as we said, there is a directed edge in the induced graph G rho from P to Q if and only if the distance between P and Q is smaller than rho of P, the range that is assigned to P. In the symmetric model, there is an undirected edge in the induced graph G rho between P and Q if and only Q, both P and Q lies each one in the transmission range of the other one. The receiver-centric interference model. In this one, the interference of a point P in the graph G rho is defined as receiver interference of P to be all the points in P except P, such that the distance between P and Q is smaller than the range assigned to Q. We can see in this example that the interference of a point P equals to 3 because P lies in free transmission area of 3 points. So what is the problem? So the problem that we consider, we call it the minimum total interference problem, or for short, MTIP, which means that given a set P of points in the plane, representing the sensor, the goal is to find a range assignment rho to the points of P, such that the induced graph GP is strongly connected, and the total interference, which we denote as the interference of rho, equal to the sum of all P in P, of the receiver interference of P is minimized. So some related work. So minimizing the maximum interference is known that there is in 1D, one can always construct a O square root n interference and find an algorithm, an approximation algorithm with O of n to the quarter in the symmetric model. In 2D, it's known that this problem is NP-hard, and one can find a square root n interference in the symmetric model and O of log n approximation in the asymmetric model. With respect to minimizing the total interference, in 1D, one can compute an optimal network in O n to the 4th time in the symmetric model, and in 2D, the problem is known to be NP-complete. So our result. So we studied the minimum total interference problem, MTIP, in the asymmetric model. And the main result, which we show that one can solve the MTIP optimally in 1D in O of n to the 3rd time. And furthermore, in 2D, this problem is NP-complete. And there exists a polynomial time 2 approximation algorithm for the minimum total interference problem in 2D. In this talk, I will focus mainly on theorem 1. So given a set P of points in the plane and a range assignment rho from P to the positive R, the receiver-centric interference of P is, as we said, is all the points Q in P without P such that the distance between P and Q is smaller than the range assigned to Q, which means it's all the points that P lies in their transmission range. In the center-centric interference, we said that the center interference of P is all the point Q in P such that the distance between P and Q is smaller than rho of P, which means it's all the point that Q cover in its transmission range. And a nice observation is if we look on the total interference, which we marked as I interference of the range assignment rho, which is sum of all the receiver interference, it's actually equal to the sum of all the sender interference. Therefore, from now on, we can restrict ourselves to sender interference in this talk because the sum is equal. So we can say the problem is, given a set P of points in the plane, the goal is to find a range assignment rho to the set of points such that the induced graph G rho is strongly connected and the total interference, which is the sum of all the sender interference of P, is minimized. Okay, now we can talk about the MIT IP in 1D. So to present this algorithm, it is composed of two parts. First is computing all sync trees. Then we use this sync trees to solve the MIT in 1D. So let's start with some notation. Let P be a set of endpoints sorted on an horizontal line such that Pi is to the left of Pi plus 1. For each I and j such that j is bigger or equal than I, we denote Pij as a subset of P which contain all the points Pi plus 1 up to Pj. A sync tree T sub ij synced at I of Pij is rooted at Pi is directed tree that contains a directed path from each point P in Pij except Pi to Pi. You can see in the figure a tree Tij rooted at I that is directed towards Pi. Pi is the sync of this tree. Always the superscript is with the sync of the tree. Let rho sub ij of I be a range assignment to the points in Pij such that the graph induced by rho sub ij of I contains a sync tree Tij synced at I of Pij rooted at Pi. Symmetrically, we define it also for j. So we have a tree rooted at Pi, and we also have a tree of the subset ij rooted at Pj. To avoid notational overload, we omit the superscript from Tij and rho ij when it is equal to I. Okay, when the sync is I, we omit the superscript I. Okay, let I rho ij denote the total interference of rho ij. Rho ij is an optimal range assignment to the points of Pij if and only if the interference of rho ij is minimized. Let G, composed of the set of points P and the set of edges E, be the complete directed graph on P. For each edge Pij in E, we assign a weight. The weight of Pij is all the points that lie in the disk centered at Pi of radius Pij. Let's see in this example, the disk is 1D disk, and we can see in this example we have the disk centered at Pi of radius Pj, and all the points that lie inside this disk, which is 1, 2, 3, 4, 5, this is the weight of the edge Pi Pj. In this case, it's 5. Let the Gij be the subgraph of G induced by Pij, and Tij is the sync rooted at Pi in Gij. Let the weight of the tree be the sum of all the edges in the tree. The weight of the edges in the tree. So the first lemma claims that rho ij is an optimal range assignment to the points of Pij if and only if Tij is a minimum weight sinc tree rooted at Pi in Gij. The conclusion from this lemma is that to compute an optimal range assignment rho ij, it is sufficient to compute a minimum weight sinc tree rooted at Pi in the graph Gij. Notice that the tree, if we want to compute a sinc tree rooted at Pi, so it's not the minimal one is not that Pi plus 1 will be directed to Pi and so on. Because you can see that the weight of this tree, when everything is just going left to the first consecutive point to the left, the weight of this tree is 9, while if we do a little bit something different, then we get, for example, here, the weight will be only 7. So it's also not clear how to compute these minimal trees. So let Tij be minimum weight sinc tree rooted at Pi in Gij, and let opt_ij denote its weight. So one observation that if we look at points Pi, Pj, and Pk, we can see points Pi, Pj, and Pk, such that if Pi, Pj is smaller than Pi, Pk, then the weight of Pi, Pj is smaller than the weight Pi, Pk. Okay, this is quite clear. A lemma, for every two distinct edges Pk and Pl, so we have an edge Pk, Pl, and Pk prime, Pl prime in the tree. If K prime is between K and L, then it follows that L prime is also between Pk and Pl, when it's bigger or equal than Pk, but strictly less than Pl. On the other hand, we also have that if L prime is between K and L, then K prime is strictly between K and L prime. Okay, so to see this lemma, we will only prove bullet 1. The bullet 2 is symmetric. So assume toward contradiction that there is that K prime is between K and L prime it's not between K and L, which means that L prime is smaller than K or L prime is bigger or equal to L. So we have the edge Pk, Pl, and then this is the cases for the edge Pk, Pk prime, Pl prime, if we assume the contradiction. So first, assume there is a path in the tree between Pl to Pk prime. We will see in a second that this cannot be the case. But if there is a path in between Pl to Pk in the graph, then clearly in this case, it cannot be the case because we form a cycle and we know we have a tree. But if there is a path between Pl and Pk prime, which means that we can change the edge Pk, Pl prime to go only to Pk prime, and then the weight is smaller, which contradicts the fact that we have a path here. The same odd here, we change the edge between having the edge Pk, Pl prime, and if you remember by our observation, the weight of this edge is smaller, then we got a tree with minimum weight, and the same, but we still have a path that goes to our sinc. So we may assume that we don't have a path between Pl and Pk prime, which means that the path from Pl to Px when x is the sinc that we are looking for, that we should compute. Therefore, the path is not from Pl, does not go through Pk prime, because there is no path between Pl as Pk prime, as we mentioned. In this case, we can just change the edge from Pk prime to Pl prime to go only to Pk, and we have a path from Pk prime to our sinc, which has results such that the tree has less weight. Again, which is in contradiction to the optimality of what the tree that we had. The same true here, that we can replace the edge by the edge Pk, Pl by the edge Pk prime, get a tree with less weight, and again we got sync tree with less weight, which contradicts the minimality of the optimal tree. And the same here. Okay, so we got that this is the lemma we just proved. So bullet 2 is exactly the same. So let Tij be a minimum weight sync tree rooted at Pi in Gij, and let opt_ij denote its weight. Let Pj, Pk be an edge connecting Pj to Pk in the tree. So we have an edge between Pj to Pk in the tree, okay, and we have a tree that is rooted at Pi, okay. So in an optimal solution, we know that all the points here should form a sink to Pj. This is so the optimal sink here should be a part of all the optimal solution. Okay, so basically what it means, the Pj, Pk, this edge, partition the tree Tij into two subtrees Tij. So we have one tree here from k to I, which is Pi k superscript I. We said that we omit it when it's clear that it's I. So we have here a tree that is synced at I, and also we have a tree here from Pk plus 1 up to Pj. So if this is the edge, then it's, in the optimal solution, it's split to two trees. Therefore, opt_ij is equal to opt_ik plus the weight of this edge plus opt from k plus 1 to j. Now the sink is j. Symmetrically, if we wanted to compute opt_ji, like the optimal sink tree from Pi to Pj when the sink is j, so then it's equal exactly to the same idea. So we're looking on the edge, and we add this edge, and it's opt of ik minus 1 plus opt of j kj. So then we can use dynamic programming to solve this problem, and this would take O to the power of 3. But just considering all ij, and this is the way we compute our dynamic programming. So we saw how to compute all the sync trees. Now we will see how to use this to compute the MTIP in 1D. So to recall, we have our set of points on the horizontal line, and let's assume we are giving a range assignment rho for the set of points. So the interference rho of a point P is all the points that lie inside its range. So all the points that lie inside its range, this is the interference of one point P, not including the point P. And the interference of the range assignment of rho is equal to the sum of all the interference of all the points in P. A left range assignment for P is a pair rho L, and rho R of functions that assign each point left and right ranges respectively. So here we're going a little bit in weird way. Instead of using the range assignment, we split it to left and right. Even though it's not intuitive, we will see that this way allows us to get some structure on some optimal assignment that is restricted to such range. We will elaborate on this in the following slides. Now we're saying that giving rho L the interference of a point P is all the points that lie inside the range assigned by this rho L. And symmetrically, the interference of a point P by rho R is all the points that lie inside this range defined by rho R. So for example, if we have this rho R for P, then the interference of P with respect to rho R is all the points that lie inside. So it's this point and also these 3 points that lie inside this range of rho R. And the interference of this left-right assignment is the sum of all the points, and for each point we take the maximum among these two interference, the left interference and the right, the left range and the right range. Okay, so we're looking on the biggest range, and this defines our interference. So in observation, let rho be an optimal range left assignment, and let rho L and rho R be an optimal left-right assignment. Then clearly, by what we just mentioned, the interference of rho is equal to interference of the left-right assignment. But just because this is the minimum among all the strongly connected assignment, and here we can just take them to be equal to the assignment of rho. So this did not help us. So what we can define a little bit something else. We can define the left range assignment of rho L, the interference of the left assignment of pi, to be all the points to the left of pi inside the left range. And similarly, we can define the right range interference of rho I of point pi. It's all the points that lie inside the right range of pi. So now we split the interference to include only the point on the left and only the point on the right. And now symmetrically we can define I prime, which is the interference of this pair, to be the sum of the left interference for P and the right interference for P, and we sum it up over all P. And an optimal left-right assignment minimize I prime, but it minimizes I prime among all the assignment rho L and rho R such that they are minimizing I. This means that we take a minimum interference left-right assignment, and among all the ones that give us minimum interference for this pair, we take the pair that minimize also I prime. So just to be clear, we look on the range assignment, left-right assignment that minimize the interference, which is exactly as defined in the original problem, and among all this one, we take the one that minimize the interference I prime. So in observation, let rho L and rho R be an optimal solution. Then for every point pi in P, the left assignment of pi is ending on a point, and the same for the right assignment of a point pi, which means that it cannot land inside because in a range, because we can always take it, shrink it to the left. There's no need to increase it. So that's an obvious observation. Now we have this lemma which gives some structural property on an optimal solution. So there exists an optimal solution with the left-right range assignment, satisfying the following property. Let pi be a point. So we have a point pi such that the left range of pi is a point pj, and the right range of pi is on points pj prime. Then the first property is saying that if we have a point inside this between j to I, not including j, not including I, then the left assignment of pk cannot go behind pj, which cannot go even to j. So the left assignment of pk will be to a point which index is bigger than j. Property 2 is symmetrically, if we have a point inside this between pi and pj prime, it cannot go to the right of pj prime and not even including pj prime. The third property says that if we have a point inside, as before, then it cannot reach behind pi. Actually, it can reach pi, but cannot go behind pi. And the last is symmetric. It can go up to pi, but not behind if we have a point inside this range. So we will prove property 1 the same. The other properties are quite similar, and the proof is quite simple. So let's assume that we have such a pair. We have pk inside, and it has an edge going to pt, and pt is outside pj, and then we can just replace the edge pi pj, the left assignment of pi pj, by to have a little bit something smaller, which means pi pk. And by doing so, this contradicts the optimality of our left range assignment. a corollary from this lemma. So the first corollary says that if we have a point pi, which right range of it goes up to pj, and its left range go to a point pk, then inside here, what we have, the structure that we have, is a sink that is directed to pi, and here we have a sink which is directed to pi. So the sink starts from pj minus 1 and goes all the way to pi, and the same here. So this is the sink tree structure that we already was show how to compute. Another corollary from this lemma, that if we have a point pt, which is t is bigger than j, which is the right range of pi, then we cannot have an edge that going behind pj minus 1. So the edge, the left assignment of pt can go only up to j minus 1, but not behind this. So this helps us to have a structure for the optimal solution. So let opt ik denote the cost of an optimal solution for the points from I to n, such that, so we're looking on optimal solution for this point from pi to n, constraint, subject to the constraint that pi left assignment is pk. Okay, so we're saying opt ik is the solution, is an optimal solution for this set of points, such that pi left assignment is pk. So if I equal n, then this is a 0, because we don't need to do anything here, we are done. Otherwise, it means that there is a point inside between I and n, such that the range, the right range of pi goes to pj. Now, we can use our lemma. So it means that there exists a point pt between j and n, such that the left assignment of a point pt goes all the way to pj minus 1. And by the corollaries, we have that the left assignment of the points between I plus 1 to j minus 1, and the right assignment for point I plus 1 to j minus 1 induce minimum, okay, if we're looking on these points from I plus 1 to j plus 1, remember this corollary, they induce two minimum weight tree. This is as was mentioned here in this corollary. Now, we have that the optimal solution, opt ik, so we call that we have the optimal solution for the point from I to n, when we know that point pi goes all the way to pk, it's equal to the weight of this tree that goes from I to j minus 1, and for this point, n is directed to pi, so this tree that goes all the way to I from point pj minus 1, plus the weight of the edge pt pj minus 1, plus the weight of this tree that goes from j up to t, when the sink is t, plus the optimal solution from point from t up to n, when knowing that the point pt goes all the way to j minus 1. But we need to add something more. We need to add the difference in the interference when the point pi goes all the way to pj. So if pi pj is smaller than pi pk, then this is nothing. But if we increase the range, then we may include some more points here, but also we may include some more points here. So this is the difference in assigning the range of pi to the right to go all the way to j. Okay, and instead of going to k. So now we can use dynamic programming to solve this one, because we already computed all the trees and we computed all the sub-optimal parts, which conclude that we can compute the MTIP in 1D in n to the power 3 using dynamic programming. So that's the first theorem. Now I don't have time, so I will not go with respect to the 2D version, but the 2 version is NPR, and there is a simple 2 approximation algorithm for this problem. So thank you for listening.